webinar, I just ask you to contact our sales representatives, and then they will pass over these questions to me. If this will be a lot of them, or just a lot of people would like to see like reply on the same things, we will maybe arrange just another webinar based on your needs. But now we gave 3 minutes for all people who wanted to join and was a little bit late to join. Now I'm going to share the screen, and just let me know when you're going to be able to see it.
Yes.
Okay, so we have 4 main topics to cover today in regard of heat exchangers, braze heat exchangers. This will be surface margin, which to which we'll dedicate most of the time. And I will be having some slides, and later on I will go to selection software itself that we can take maybe a few examples from real life, and you see how to simulate different behavior of the heat exchanger in selection tool. Then we'll discuss a little bit about the braze heat exchanger failures, what are main reasons for that, how to basically increase the lifetime of the brazed heat exchanger. A few words about our new coming selection tool, Hex Selector, which will be available in 2021. And as I said, questions and answer session. So whatever information I will present, if you have any question, type in the chat straight away. And in the end part, we will discuss them. Before I will go to the surface margin explanation, I would like to remind you the basic heat transfer equations, which I'll be referring to along the process. And if you will need more actually on these heat transfer equations, we had held a webinar in the beginning of this year specifically addressing heat transfer equations and what depends on what in heat transfer process. Recording of this webinar is still available. You can ask for it, or again, you can Google all the information you want in the internet right now. So the basic heat transfer equations I'll be referring to will be a general heat transfer equation, which links amount of heat you would like to transfer with the heat transfer coefficient, heat transfer area, and logarithmic mean temperature difference, LMTD. LMTD is basically describing as what is average temperature difference between two medias, hot and cold media, heat exchanger. Then one of the most important parameters is the heat transfer coefficient, HTC, which depends on the film coefficients on both sides of the heat transfer surface and the heat resistance of this heat transfer surface. And in most general way, our film coefficient is depending on the velocity of the flow in the channels. Another set of equations we need to talk about is the laws of energy preservation, which links amount of heat given by one side, with the mass flow rate of this media, with the specific heat capacity and temperature difference on the inlet and outlet for this specific media. This equation is always written for both media, so for hot and cold. And in heat exchangers, we normally consider that these two amounts of heat are equal, so we don't lose any heat to the atmosphere. Heat losses are assumed to be zero. Next set of equations is a continuity equation, which is linking mass flow rate to the density of the fluid, cross-sectional area, across where actually this mass flow rate is going through, and velocity in the channel. And this is also written for both sides, so for cold and hot side. And then one last parameter we'll be referring to will be a pressure drop, which, let's say in most general case, depends on your velocity in square, and then the geometry of your channel where the liquid is going. So now, after we refreshed these basic equations, I'm going to tell you specifically about surface margin, how it appeared as a demand basically in district heating networks, why it appeared, and how this surface margin is behaving in plate heat exchangers specifically. In most general, you can say setup, in any liquid to liquid heat exchanger, we have 3 stages of heat transfer. This is convective heat transfer from media to the heat transfer wall, then heat conductivity in the heat transfer surface, and then again convection from the heat transfer surface to the cold media. When the heat exchanger is being used for some time, of course, all the particles or any like chemicals which are dissolved in the working medias, they start depositing on the walls. By this, adding 2 extra, you can say, heat barriers along the heat transfer process. That means we add 2 extra heat conductivities between convection 1 and convection 2. In mathematical way, it simply means that in our regular heat transfer equation, which for clean heat exchanger is mentioning only the resistance of the plate between 2 medias, yeah, we need to add another actually member of this equation, which will be the resistance of the dirt. And you clearly can see that if we add more members of equation in this bottom part, our heat transfer coefficient is going down. What it means for my load needs to go down if all the remaining parameters are kept the same. In order, what means the heat capacity or amount of heat will go down? That our user will not receive as much heat as he wants or he needs. Yeah. How we can compensate it? HVAC systems in most general way are like self-compensating systems. Yeah. So if there is not enough heat somewhere, the valve will open, and that in most general case leads to increase of LMTD. So if we have reduction, can I ask to mute microphones? Thank you. So in most general way, if we have reduction of the heat transfer coefficient, LMTD, logarithmic mean temperature difference, needs to be increased. That means in most general case for district heating applications that our primary outlet will start increasing. Yeah, and by energy preservation law, if my primary outlet starts increasing, that means my delta T for the primary side, inlet and outlet, basically decreases. And in order to transfer the same amount of heat, I need to compensate it by increasing of the mass flow. I'm not now talking about specific applications where we can have flow limiters and something like this. It's just how the mathematics works, yeah? And in most general way, if we make a temperature graph for some application, let's say in Central Europe, where we have a bit lower supply temperatures, if we designed our system for 80 to 60 degrees on the primary side and our heat exchanger starts getting dirty, that means that my primary outlet will start getting increased, yeah, maybe to 65 degrees, together with the increase of the mass flow. Both these things, increasing primary return and increasing mass flow rate, are actually harming efficiency of the district heating setup in general. That's why very long ago there was already appearing a recommendation of so-called surface margin. Before going deeply in this, I want to give you just a small history which type of heat exchangers were used before, yeah, in district heating appliances. These were shell and tube heat exchangers. These heat exchangers have a very long history. They're still being used now mostly in industry. But how they were designed? They were standardized. So all these heat exchangers were not tailor-made. They had a standard catalogs where you select your heat transfer unit from. And all shell and tube heat exchangers were, in general, having standardized shell diameters, yeah, length of tubes, and the number of tubes squeezed in this specific shell diameter. As you see here on the right part of the slide, there was different ways how the tubes can be arranged in the shell. And then, as long as these were standard, actually, catalog items, by shell diameter, tube diameter, alignment of the tubes, distance between the baffles. Baffles are these supports here, which were actually supporting the tubes, and number of tubes. The designer was able to calculate the cross-sectional areas on the shell side and on the tube side. Out of a cross-sectional area for the flow, the velocities were calculated, and out of velocities, the film coefficients were calculated. Out of film coefficients, using the heat, basically the heat transfer coefficient calculation formula, which I showed on the previous slide, the heat transfer coefficient was obtained. And after that, designer was simply performing a checkup if his basically main heat exchanger equation is being closed in the right way. So if with this heat transfer coefficient, which he took for this heat exchanger, and the logarithmic mean temperature difference and the heat transfer area, he can transfer the amount of heat required. If yes, he was in general taking this heat exchanger, yeah, but if not, then he had to take another type of the heat exchanger. So if there was not enough heat transfer area, or this heat transfer area was not corresponding to the demand of the district heating network in terms of this surface margin, the designer was taking simply the next standard heat exchanger from the catalog, which in most general case led to simply taking the same diameter of the shell, same number of tubes, same type of the tube pack, just longer tubes. And what was the benefit of doing that? The cross-sectional areas were the same on the tube side and on the basically shell side, meaning that velocities were still kept the same. That means film coefficients were still kept the same. And that means my heat transfer coefficient was still constant. So in the shell and tube heat exchanger, when I was adding extra length of tube, I was really just simply adding surface margin. So if I had, by the calculation, have selected originally the heat exchanger on the top, let's say 2 meters length of the tube, and on the bottom 2.5, that simply means that these extra 500 millimeters of tube are really just a surface margin, because my heat transfer coefficient remains the same. And this is not a case in plate heat exchangers. Why? Because here you see a cross-sectional area of heat exchanger. This is XB37 from our range. And in this heat exchanger, half of the channels are for the cold media, half of the channels are for the hot media. Yeah. So what happens if I'm starting putting extra surface in a plate heat exchanger? Let's imagine I originally have designed a unit with 20 plates, and then because of surface margin demands, I would like to have a 40 plate heat exchanger. If we will write these continuity equations for both sides, we see that simply by increasing the number of plates, I increase number of channels. Yeah, by increasing number of channels, I actually increase my cross-sectional area for the flow. And by doing that, if I still have my constant flow rate, which I have, and we can also say density is also a constant, my velocity will go down. So by increasing number of plates in plate heat exchanger, I'm dropping velocity in the channels. If I'm dropping velocity in the channels, I'm actually dropping film coefficient. And as you have seen before, film coefficient has direct impact on the heat transfer coefficient. So it also goes down. That means in a plate heat exchanger, more plates you add, yeah, you artificially then worsen your heat transfer coefficient because of dropping velocities in the channels. And that's also the reason why in plate heat exchanger, in reality, surface margin is not surface margin as it was like before in shell and tube units. It is a heat transfer coefficient margin, because how this is calculated in any selection software for plate heat exchangers, it's simply a ratio of your available heat transfer coefficient to your required heat transfer coefficient. And here I have just a small screenshot of our Hex selection tool, where you see heat transfer coefficient, and there are three values separated. So it's available, service, and required. So, and surface margin is calculated as available to the required. Yeah, in our case, it's 6,400 in ratio to 5,700, which gives us 13% surface margin, which you see here. What is service here in between? In case you already know that there will be certain thermal resistance or dirt accumulated on your plate, you can put this exact value of this dirt in the selection tool, and this will show you so-called a service heat transfer coefficient. But in 99% of cases in HVAC industry, we never do this input. We never do this input for the selection tool. That's why you will always see your available and service heat transfer coefficients are the same. Yeah, if we go to industry applications, some, I don't know, oil cooling or anything outside of HVAC, then sometimes we use this service heat transfer coefficient. On top of this, I would like to just clearly visualize for you how the surface margin impacts the heat transfer coefficient values in the plate heat exchanger. Just to prove you that with the increase of surface margin values, we drop the heat transfer coefficient. Here you see a typical duty I took. It's just domestic hot water, summer conditions, 120 kilowatt. And I dimensioned it for a couple of sets of surface margins. First thing, please mute your microphones. Okay, thank you. As you see, first thing I would like to address, the brazed heat exchangers, brazed plate heat exchangers. These are standard type of goods, meaning they are produced with a discrete number of plates. So 10, 16, 20. That means we have a step of plates like 4, 6, or 10. That means you will always have a small surface margin when you make a selection of a brazed heat exchanger. Just because the software will automatically select, of course, the closest standard unit from the catalog, which will be like in case you make selection and you need 18 plates, it will take 20 plates, rounding up the heat transfer surface, of course. And by this, you will always end up with the heat transfer coefficient or surface margin coefficient is bigger than you actually originally put it. But now let's simply check one thing. If I was dimensioning with a 0 requirement for surface margin, I received XB37L with 20 plates and heat transfer available coefficient 7,200. More I go increasing the basically surface margin demand, you see that more my heat transfer coefficient is dropping. That's the impact of this decreased velocity in the channels, which I was just showing to you. But in general, surface margin, it's a quite complicated thing, and we can normally split the surface margin types in 3 main groups. And each of groups has different impact on your system. So for example, surface margin type number 1 will be related to highly asymmetric flow rates on primary and secondary side with a high logarithmic mean temperature difference. So a good example will be here a floor heating application with a high supply temperature. Floor heating now is becoming more and more popular, and I want to highlight what I mean by asymmetric flow rates. If you check the capacity here, 100 kilowatt, yeah, and on the primary side we have design conditions 100 degrees inlet, 60 degrees outlet, and on the secondary side we have 35 degrees inlet, 42 degrees outlet. You will see that difference in temperatures on the primary side is 40 degrees, and on the secondary side is just 7 degrees. Yeah, by the energy preservation law, which I was showing before, this clearly links your delta T to the flow rate. And if you will check here, you see that on the secondary side, you have like 12 1,400 liters per hour, or this is like 12 cubic meters, yeah, versus 2,000 liters per hour on the primary side. And you see the flows here differ a lot, so 6 times more or less, and that's what we call asymmetric applications. Asymmetric applications are usually the reason for your surface margins, for your too high surface margins. And in that case, let's see, I have 695% surface margin for my selection. Why it is happening? Because I have very high flow rate on the secondary side. Yeah, and I have just 15 kilopascal pressure drop allowed for this high flow rate. That means when my selection software is making calculation, the limiting factor here will not be a thermal efficiency of the heat exchanger. It will not be like anything related to the pressure drop on the primary side. It will be simply limited by the pressure drop on the secondary side. And after I will classify all the surface margin types for you, I will show this specifically in the software, yeah, how to see it and understand which side is the limiting one. In most general case, if I want to understand what is the impact of my 700% surface margin, I need to calculate this heat exchanger with the real outlet conditions, meaning that I need to perform a so-called performance calculation of the heat exchanger. Here, there are 2 ways of doing that. It's either in a selection tool, you go to performance mode, yeah, and then you do the performance calculation, or actually I will show later on, you can use our real outlet calculate feature when you simply perform the design of the heat exchanger. But what's most important, yeah, if I do the performance calculation tells me exactly how my surface margin will impact real behavior of the heat exchanger in the real system. And I see that instead of, if I simulate the performance of real system, instead of 700 degree surface margin, I will end up with 1.7% surface margin, but my extra surface, which I have in my heat exchanger, will be impacting my primary outlet. And instead of 60 degrees, which was my design conditions, I'll end up with actually real outlet 35 degrees. And as you know, by energy preservation equation, if I'm increasing delta T for the media, yeah, I can drop the flow rate. And look what happened here. Instead of my 100 to 60 and 2,200 liters per hour flow rate, my real system will be working 100 to 35 and just 1,300 liters per hour flow rate. So what that means? That means I need to select my control valve for this heat exchanger using this flow rate, not the one from design conditions. No, because it doesn't consider that the fact that you have surface margin. You need to make a simulation, get this real flow rate, and that is your flow rate for valve selection. So, and you see the impact here, it's already 2 times different flow. If somehow I made also a rounding up of the valve which I selected, then I have clearly overdimensioned valve, which then might actually lead to big control issues in the system. So here, this is one type, quite often met, because, and it also creates a lot of confusion because it usually gives 100. So what you need then to keep in mind for these kind of cases is simply to make calculation in real outlet conditions or in performance mode. Next type of the surface margin I would like to show you is surface margin in district heating with high supply and low secondary side outlet radiator system. So highly asymmetric flow rates, still highly asymmetric flow rates, but much lower temperature difference between primary outlet and secondary side inlet. This is, if I'm not mistaken, a quite typical for Baltics heating design conditions. 115 in, 53 out, 50/70 on the secondary side. Here, as you see, by my calculations of the flow rates, it's still quite asymmetric, meaning that on the secondary side, I have close to liters per hour. On the primary side, I have close to 3,000, so it's 3 times difference on the flow rate. That means all my heat exchanger dimensioning will be limited by hydraulical factors on the secondary side. I will show you later that. Here you will never end up with the surface margins of hundreds percent. It will be maybe 20, 30, 40%. And the impact on your system will be more or less the same. So in order to understand how the surface margin is actually transferred to the maybe some change of design conditions of your system, you need to make a calculation in real outlet mode. And what you will see here, as long as my design temperature primary outlet 53 degrees is already not very far from my secondary side inlet 50 degrees, yeah, simply by the heat transfer logic, I'm not able to drop the primary outlet lower than my secondary side inlet. That's all my surface margin is transferred to dropping the temperature just for 2 degrees extra compared to my original design conditions. And that means 2 degrees temperature difference in design conditions and real conditions. It doesn't impact your flow rate at all. I mean, of course, a little bit, but this is inside any valve will take this kind of deviation of the flow easily. So that means if you have this type of surface margin, yeah, so you receive 30, 40% somehow, and you have very low temperature difference between primary outlet and secondary inlet, you basically don't need to make any activities to recalculate the flow rate and change maybe your valve. Here, it's not needed because it's simply possible to overcool it any more than secondary inlet. That's why it will have very small impact on the flow rate. But I will remind you, in the first case, which we had, my temperature difference between primary outlet and secondary side inlet was 35 degrees. Yeah, and this, of course, delta T of 35 degrees, if I overcool the primary side, creates a big impact on the flow rate. This you have already seen. Now, I will say in general, these two types of surface margins are basically only leading to the control, if you don't consider it, might lead to the control problems in your system. But it's nothing about like we should keep in mind about self-cleaning of the heat exchanger or something like that, because heating heat exchangers, yeah, is it radiator heating or floor heating? They are normally working with the closed circuits, yeah, and with heat treated or chemically treated water. That means once the circuits are filled in, yeah, the water there is not being refreshed sometimes for years. That means when I have surface margin in heating applications in closed loop systems, I more or less don't care much about the impact of my surface margin on self-cleaning and on any velocities in the channels, because these are relatively clean medias, and I don't need to think about self-cleaning of the heat exchanger. But that's completely different for type 3 of surface margin, which is basically for us meaning the surface margins in domestic hot water applications. This is very challenging because these domestic hot water applications, they are usually having high seasonality. Yeah, this we know, because they are designed for summer conditions. But then most crucial actually is then working in winter conditions. And what improper design of the system can lead to is simply over-dimensioning of your domestic hot water control valve, and by this having issues in control quality, which together with really challenging water quality usually on the domestic hot water side, which is an open loop, yeah, and this is normal water coming from water supply plants, can lead to failures, and actually is leading to failures of the heat exchangers. What we need to know about surface margin in applications for domestic hot water. When we design a heat exchanger and we put, let's say, 20, 30, 40% surface margin for summer conditions, this value is automatically doubled for winter conditions. So that means if you dimension the unit with the 25% surface margin in summer, it will work with the 50-60% surface margin in winter. Why it is happening? Because your logarithmic mean temperature difference will be different. Yeah, it will increase for winter. And now we'll look simply a comparison of your design conditions. So here is a just same application I was referring to. Summer, 70-25 primary, 10-50 secondary, 20-20 kilopascal pressure drop. That's our design. When I design a heat exchanger and I make recalculation of this heat exchanger in real mode, yeah, how much my surface margin is then transferred to change of flow rate to the primary, it's just 300, you can say, kilograms difference, yeah, which is not critical for a control valve. But when I make a real checkup of performance in winter conditions, when basically in winter conditions, my secondary side temperatures are remaining the same, so 10 to 50. Yeah, my capacity remains the same. I have same amount of users, but my inland temperature from district heating network actually increased a lot, so from 70 to 110. That creates like effect of doubling the surface margin straight away. And then this doubled surface margin create effects of course, overcooling the primary side. Look, my temperature on the primary is getting really close to my secondary side inlet. Yeah, that's what we already seen in the effects of surface margin type 1 with the floor heating. And look at my flow rate in winter. This is 1,000 kilograms per hour versus 2,300 kilograms per hour in my design conditions. So, and this is in full load. If I'm dropping this load, let's say to 1-2 tappings, yeah, just only one consumer or two consumers, the flow I will have here will be close to 100 kilograms per hour. And that's very important to consider when you are making calculations for domestic hot water systems. Because the flow rates and your outlet temperatures are really different in different scenarios of usage. And actually, most critical application where heat exchangers, brazed heat exchangers are mostly failing is domestic hot water and domestic hot water during winter. I will show you now in the selection tool specifically the impact of actually different scenarios. First, I would like to address specifically the surface margin and the temperature graph, which was sent to me as a question that, for example, in Lithuania, yeah, there is standard heating, 110 degrees inlet, 60 degrees outlet, and 50 degrees to 70 degrees on the secondary side, with a capacity of 300 kilowatt. So here I made this selection. And now I want to highlight your attention basically on how to identify what is the limiting factor in my heat exchanger selections. Let's check it out. As I was telling to you before, we need to see what is delta T on the primary and the secondary and check my flow rates. Here I see that flow rate on the secondary side is 13,000 kilograms per hour, which is much higher than flow rate on the primary side. That means I will have higher velocity in the channels on the secondary side, and I will have higher pressure drop on the secondary side. I made here already the selection, and you see that the real pressure drop in my heat exchanger basically confirms that. I have just 3 kilopascal pressure drop on the primary and 16 kilopascal pressure drop on the secondary. And I'm not even reaching my 20, yeah, here. That creates, together with the impact of very high mean logarithmic temperature difference, which is 21 degrees, that's actually considered to be high LMTD. We usually say it's high if it's above 10. It's medium from 10 to 5. It's low if it's lower than 5. And how now to understand what will be the impact of this surface margin to my calculation? Yeah, I need simply to calculate using not calculate button, but real outlet calculate button. What will change? Now let me press this one. My selection software now will make a calculation utilizing full surface margin. You see, I have no surface margin anymore. My surface margin is 0 because selection software calculated full impact of using whole surface on my parameters. And now I see that instead of 110 to 60 degrees on the primary, and instead of 5,000 kilograms per hour mass flow rate on the primary side, my XB52M here will end up outlet and flow rate of 4.3 like tons per hour, or 4,300 kilograms per hour. So in that case, my surface margin, which was 100%, is actually a full benefit to district heating network, because I am providing back to the district heating lower temperature than they want, so below 60, and I'm actually using lower flow rate from the district heating supply system. That means that this surface margin in this case is completely safe thing, and it only gives a benefit to the whole district heating network. But what I need to take into consideration, the fact that my surface margin changed my primary outlet from 60 to 50, and I need to use now for design conditions of my welf, this flow rate, 4,300 kilograms per hour, not the flow rate from 10 to 60, which will be 5,100 kilograms per hour. So that's the impact of the surface margin in this case. It's just increasing efficiency of whole district heating setup. Just keep in mind the flow rate on the primary is decreased, and you need to take another welf for that. Now let's address the domestic hot water applications. Yeah, and I want to show you how in domestic water applications we can face different scenarios of usage. I dimensioned here 420 kilowatts, 1050 secondary, 7040 primary, and 2020 kilopascal pressure drops. In this case, I see that my actually limiting side will be the primary side from hydraulic perspective, because it has higher flow rate. Yeah, and if I'm calculating just in design conditions, you see I'm getting 26% surface margin, and I'm getting like 70-40 degrees on the primary side. Let's again try using real outlet calculate temperature. What I will see now, my heat exchanger, which was selected before, yeah, with 26 plates, now is selected with 0 surface margin, and I see that instead of 40 degrees, I'll be having 32 degrees, and I will have actually decreased flow rate. Yeah, 2,700 versus 3,400. So here, it's always important to make a selection in real outlet calculate to see how much your surface margin really impacts the selection of the welf. And proper selection of the welf on the primary side is actually increasing the whole reliability of the system, and also prolonging the lifetime of the heat exchanger. I will later on describe you how actually this happens. One of the most important things I want also to highlight is the fact that domestic hot water capacities also need to be calculated in the right way, because we are still using sometimes district heating network recommendations or regulations and norms, which lead to a serious over-dimensioning of the domestic hot water design capacity. And I would like basically to go back to my slide deck just to briefly show you that. If we look in the norms of district heating, let's say for all the countries which are coming from ex-USSR, that means Baltics, like Ukraine, Belarus, Russia, mostly the norms specifying the domestic hot water consumption are saying us 60 to 70 liters per day of hot water per one person. And this was originally coming because we use domestic hot water for washing dishes, and then for bathroom, shower, of course, kitchen sink. And fact is that right now in modern systems, basically washing clothes and washing dishes is right now done by separate devices, your dishwasher and washing machines, which are connected to cold water supply, not to hot water supply. So they consume cold water, and they have their own heating elements. That means that in real systems, what we see right now, the amount of water consumed basically dropped twice to the design conditions. So we have 30 to 40 liters per day of hot water. And this, of course, needs to be taken in consideration when new buildings are being designed, because if you make over-dimensioning of the capacity, let's say you have to make the selection and by the regulation you need 300 kilowatt of heat load, whether in reality customers are consuming only 150 kilowatt of heat load. That's doubling of your surface margin for the heat exchanger, and that's doubling your basically safety on the valve, because the valve was selected for twice bigger flow rate compared to what you need. And then that's really, you can say, a trap which can be easily seen in designing of the systems, because if I have calculated capacity with safety and I have selected the valve for this capacity, and on top of this my heat exchanger is having surface margin, all these safety margins multiply and lead to basically very bad control of the system in winter specifically. And winter mode is very, very actually crucial for the braze plate heat exchanger. I will tell you in a couple of slides why. So what to do, yeah, in this regard of decreased capacity and consumption? The easiest way of calculation is using the norms and regulations of these flat stations. These small flat stations, which are installed individually in each flat and have a heat exchanger for preparing domestic hot water, specifically, you can say at consumption, yeah, at user himself. In most general way, for a flat, you can calculate for a kitchen, for a flat having one kitchen, one bathroom, approximately 35 to 40 kilowatt of domestic hot water. Yeah, and this 35 to 40 kilowatt, you need to multiply, of course, on the amount of flats you have, and then to use a coincidence factor. This coincidence factor you can use from actually flat stations, like recommendations right now. I'm just showing you here a graph which you can easily also find in the internet. It refers to mostly like there is a Danish and Swedish factors which they empirically calculated for big multifamily houses. And you can see a simple basically way of understanding this graph. So here are your number of flats. Here is your coincidence factor. So let's say if I take 35 kilowatt per one flat and I have 100 flats, that means capacity is 3,500 kilowatt, and this capacity I need to multiply on my coincidence factor, which is 0.1. So for 100 flats of consumers where it's one kitchen, one bathroom, I need approximately 350 kilowatt domestic hot water heat exchanger. So if you receive 500-600, that's of course a threat to stability of the system, and that's of course a threat to the lifetime of the heat exchanger. So now I would like to say a few words about basically failures of the heat exchangers. Failures of the heat exchangers are, let's say, if I split all the failures of the brazed units, 97% of failures are happening in domestic hot water applications, and they're mostly happening in winter or right after winter. Why it is so? Because we have accumulated effects of a couple of things. First, in many cases, the valve design might not be done in the very correct way. So that means, as I was explaining to you before, it's either I'm working with a much lower real capacity than I designed my valve for, or I'm working with a huge surface margin of the heat exchanger. It doesn't matter what actually is the main reason. Usually you have a little bit of surface margin, a little bit of oversized valve, but altogether it leads to the fact that in winter, especially in partial loads, I will work in the range of valve, which is basically opening and closing. Yeah, or not completely opening and closing, but really pulsating the flow on the primary side. And I will remind you that in winter we have like 100 to 10 degrees supply temperature from district heating network. And 5 degrees or even 2 degrees in the winter, the cold water can be really cold, on the secondary side. So if I have a valve in working, a control valve working in oscillation mode, meaning it closes, opens, closes, opens. For heat exchanger, it creates oscillation of temperature. So heat exchanger gets very, very hot to 110 degrees. Yeah, then that leads, of course, to overheating of the secondary side. Controls immediately send a signal for the primary valve to stop actually this flow rate, to limit it, to close it. So the flow rate is closed on the primary, the heat exchanger from 100, but the tapping on the secondary side is still continuing. Yeah. My average temperature of the heat exchanger is dropping to the cold water temperature. That meaning that during one tapping, that's what we have seen actually. During one tapping, which is classically like, let's say, showering, yeah, it can be like 2-3 minutes, sometimes longer. We easily can see that the average temperature of the heat exchanger is changing from approximately average 100 to average 20 degrees, so delta T 80 degrees, close to 15 times. This like way of operation is creating huge thermal fatigue stress inside of the plate and inside of the brazing joints. That's why this thermal fatigue actually weakens the brazing point. Yeah, and if system is designed either with big surface margin, which is not considered for the redimensioning of the valve, or the valve itself is basically calculated also with the safety, leads to thermal oscillations in winter, especially in partial loads. Thermal oscillations lead to thermal fatigue issues. Thermal fatigue issues weaken our brazing joints. And on top of this, we have another process which even worsens the whole setup, which is called galvanic corrosion. The thing is that the most often used brazed plate heat exchanger will be brazed with copper and heat plates made of the stainless steel. If you see simply by that chart, yeah, you can understand that basically in our case, copper will be dissolved because that's like a galvanic pair. As soon as you have anything which conducts electricity, basically touching stainless steel and copper, it starts corroding immediately. The speed of this corrosion will depend on the electrical conductivity of your water. So that means in most general case, we will have a very challenging situation for copper brazing material on the side where you have your cold water, which is turned out to be a hot water. Because high electrical conductivity means just simply presence of a lot of different chemicals in the water, because the pure water itself, H2O, it doesn't conduct electricity because it doesn't have any ions to conduct electricity. But as long as we have any additional chemical parts in this water, it becomes conductive. The more conductive it becomes, faster copper will be eaten away. And of course, faster the copper is eaten away, faster the failure will happen. So here I have two accumulated effects. First, I need to make sure my basically water, let's say, is not aggressive, yeah, or my brazing material is somehow resisting this aggressive water. And second is, I need to select my valve properly, not to lead the domestic hot water system to thermal oscillation mode. And that means I need to consider carefully my surface margin impact on the behavior of the heat exchanger and real flow rates in winter, and using these flow rates for my designing of the valve. And on top of this, of course, I need to double check if my capacity of domestic hot water is selected properly. So what we do from our side in order to address these issues of exchanger failures and how to prolong the lifetime. Of course, we cannot in many ways impact specifically the like valve side if there's like some system designed by somebody else. But we can impact the brazing material. So we can make a brazing which will decrease or even completely remove electropotential difference between heat plates and the brazed material. So what we did from our side is introducing to the market two additional brazing materials, which are called co-resist and stainless steel. Co-resist material, this is a copper-based material, which actually has much bigger resistance to electrical conductivity, because by adding, changing the chemical composition of the brazing steel, keeping copper as the biggest part of it, we actually reduce electropotential difference between stainless steel and between the brazing material. And what you see here, the most critical part, conductivity in microsiemens per centimeter. The copper-brazed units can work comfortably up to 500. Yeah, the co-resist can work actually up to 1000. So if you have your cold water or domestic hot water with high electrical conductivity, the solution for you is co-resist or stainless steel. Because in stainless steel, we have heat plates and brazing material that's chemically same composition. That's why galvanic corrosion is not happening there at all. And whatever electrical conductivity of water you have, you can use these units. Of course, it's different price. So co-resist is a little bit more expensive than copper, but stainless steel is more or less, you can say, an average 2.5 times more expensive. But then completely eliminates corrosion issues. And now this is widely used in Central European region, the stainless steel brazing for domestic hot water applications, specifically in regard of electrical conductivity and galvanic corrosion problems. Mostly the corrosion problems are referred to copper or brazing material being flushed away. And then together with the weakening of the brazing joint by the thermal fatigue, yeah, the basically heat plate, they break off one from another, and then the heat exchanger cannot hold pressure anymore. So that's the typical mechanism. But also we need to be careful in regards of free chlorine, which we have in water, because then it doesn't matter what type of brazing material we use. Free chlorine is aggressive to stainless steel and creates pitting corrosion and stress corrosion cracking issues for stainless steel material. That's why it doesn't matter which brazing I have. If I have more than 1 milligram per liter of chlorine, so if somebody is chlorine treating water for making it disinfected, I'll definitely have issue with anything which is made of stainless steel. And it's not only free chlorine I need to look at, I also need to see on the chlorides, so any chemical compositions which are consisting of chlorides. For chlorides, I need to be very careful about working temperature, because as you see, chlorides allowed in the water depend on the average application temperature. But what you need to consider, if I have a if I have a secondary side 10 to 50, yeah, and I have 400 milligrams per liter of chlorides, it's not acceptable. Because you see by this table, it maybe can be a bit misleading that if I have application less than 50 degrees, yeah, which we can say, yeah, but my domestic hot water is not, it's set up to be 50, so it's less than 50. My allowable concentration of chlorides are 400 milligrams per liter. No, what we need to consider is average wall temperature of the heat exchanger. And the average wall temperature, of course, is always higher than your set it up domestic hot water temperature, because the heat needs to transfer, yeah, from more hot surface to something more cold. That's why if I take, let's say, a classical winter case, yeah, when my supply temperature will be 100 to 110 degrees, that means on the upper part of the heat exchanger, my temperature of the heat transfer surface, yeah, of heat plate will be around 80 or more than 80. That means in winter, technically, because of higher supply temperature and higher average wall temperature, you see my maximum chloride concentration should be limited to 200 milligrams per liter. So to conclude, in general, brazed heat exchanger failures, yeah, that depends on full set of parameters. So let's start maybe from the slide I see here. It starts with water. Your water needs to be either having low amount of chlorine, chlorides, and low electrical conductivity. Then you can use a copper brazed unit, or it can has a higher conductivity. Then you need to use a co-resist or stainless steel for that. Yeah, so it's simply on the water side to reduce corrosion effects, because corrosion weakens the heat exchanger. Then on top of this, you need to properly design your system in regard of consideration of the surface margin on the primary side flow rate. And you need to make a valve selection using that flow rate, of course. On top of this, you need to properly calculate capacity for your domestic hot water application, not over-dimensioning it, because in modern systems, we see the real domestic hot water need is dropping twice compared to what some norms and regulations are advising to us. And here, I'm not even touching the whole topic, how to properly select the valve, because that requires another webinar. So what I'm addressing to you is just select the valve using proper flow rate on the primary side. In regards of other recommendations, how to make system more stable, which valve to select, pressure dependent, independent, and set up for summer and winter, that's the whole topic for a different webinar. So now I'm basically done with the main part of the my presentation. Yeah, and what I would like to show you right now before we go to questions and answers is just few tips and tricks what to do when we have asymmetric application, which is limited by the secondary side. And I will again refer to the temperature graph of the radiator heating system, which I was asked for. And I want to highlight you one important part. If you have an asymmetric flow rate, which is limited, which has a much higher flow rate on the secondary side, as I said, your heat exchanger selection will be limited by hydraulical factor on the secondary side, by the pressure drop on the secondary side. And in most of cases, when we are designing a system, the most critical pressure drop for us is actually a primary pressure drop, because this is a pressure drop from a district heating network where we should be quite strict on what we have. Yeah, secondary side pressure drops are usually not an issue, because we have some pumping capacity with safety, or maybe it's even a new building where I can select just a little bit more high pressure pump to maybe optimize the whole performance of my system. Why I'm saying that? Because look what happens if I simply, instead of 20 kilopascal on the secondary side, I will put 25 kilopascal. I'm dimensioning right now the heat exchanger, and straight away, I got 10 plates less for my solution. And look, I actually asked for 25 kilopascal pressure drop, but in reality, I have just 22.10. So by increasing my secondary side pressure drop on 2.1 kilopascal, which is even unmeasurable, I will say, in a real system, I dropped down number of plates for my heat exchanger on 10 plates from 60 to 50. So I made a heat exchanger cheaper. Same time, by reducing number of plates, yeah, I actually increased the velocity on the primary side. Yeah, and I'm having right now a bit higher pressure drop on the primary side. It's not 3 kilopascal as it was before, it's now 4. And by this also, I a little bit improved the heat transfer coefficient. So by playing with the pressure drop on the secondary side, I can increase the efficiency of my heat transfer process and actually make the whole appliance cheaper. That's why when you have designs of the systems and you see that you are limited, when you select your heat exchanger, you are limited by the secondary side pressure drop. Maybe it's not critical side and you can actually add few extra kilopascal there. Yeah, maybe I can go even bolder. Let's make 30 kilopascal on the secondary side. What happens now? Yeah. And now I dropped even, let's say, to a smaller frame dimension of the heat exchanger, which actually has a little bit lower surface margin than my original XB52, which means a lower impact on the valve dimensioning. Yeah, and I'm actually having a cheaper heat exchanger, because by price list, XB12 is just much cheaper than XB52. So my advice here to you will be, don't take like completely as granted same pressure drop on both sides. Because when you have a symmetric application, as you see, I just showed you a very simple example. By just 2 kilopascal extra, I can make my heat exchanger already smaller and cheaper. Yeah, if I add even more, like 8 kilopascal, I make it much cheaper. So please look on this as well when you're dimensioning the systems, because what is happening is you have the primary pressure drop is increasing. And for heat exchanger, it's always better to work with a higher pressure drop than with lower pressure drop, just because pressure drop is directly linked to velocity. Yeah, if I'm having more pressure drop, I'm having more velocity. If I'm having more velocity, I have a higher heat transfer process on that side. So that's it, what I wanted to share. Now, then we are going to questions and answers, and I will look in the chat if there are any questions so far. And I see nothing. So please use your chance right now, or maybe Marco, Agris, Gintaras, maybe you received some questions from people before that I can reply right now. Just then type them in and I will highlight it.
Hi, Mark. Here is Agris. About the Hex Selector you didn't touch today.
Oh, yes, thanks.
And one additional question, will there be some kind of Revit designings or drawings in this new software?
Yes. Okay, so I'll start with the Hex Selector itself. Thanks for reminding. I have prepared the window here, completely got dragged away by the surface margin discussion. So we are releasing in 2021 a new selection software, which will be called a Hex Selector. And the idea behind developing a new selection tool is the fact that Danfoss acquired Sondex 3 years ago, actually 4 years ago. And Sondex had its own selection tools, which were named PHE Calc. And Danfoss has its own selection tool, which is called Hexact. And of course, in terms of unification of portfolios and reducing complexity for the designers, we want to have both types of heat exchangers available in one tool. That's why for the last, actually quite some time, it's 2 years, very active work of merging the two calculation engines in one. It was like fully reworked and optimized also for the future trends. This will be basically you install it on your computer, this selection tool, but it's addressing server, yeah, for getting all the heat transfer data, pricing data, and that's why it's always up to date. And it will have, which is most important, all Sondex and Danfoss models at one place. Meaning that right now I'm just showing you the graphical interface for the gasket selections, where I made just some cooling duty selection. So you have all the list of units which are suitable for that. And as well, you have all the Danfoss and Sondex brace heat exchangers also at one place. So in case you have some duty where actually a Sondex heat exchanger fits better, you will see it in the list right now. The estimated release time for us will be approximately Q2 2021 for external users. Right now, we're actively testing this software by actually Danfoss employees. And as long as we are sure in the high quality, like of this selection tool, we'll also send it out and make it available for external users. There will be separate dedicated trainings on that, how to use it, what's the difference, and some tips and tricks, of course. But what important part we targeted when creating this tool is whatever you had in PHE Calc, or whatever you had in Hexact, you as well will have in Hex Selector available. So that's how it works. Now, in regard of second part, Agris, of your question about Revit models, right now we have available step files, so STP 3D models for all our portfolio, and they are available on request. But Revit models will appear during 2021 in product store as well for heat exchangers. And this actually is going to both braze and gasketed. Okay. There's one question. If you optimize a heat exchanger pressure drop to reduce heat exchanger price, how much this influences power consumption of the pump over the lifetime? I mean, I don't have exactly right now a real price calculation for you, but considering that, I mean, the first step optimization I made was just 2 kilopascal, which was 10% on the available pressure drop. That's impact, I'll say, close to be unmeasurable. Together with more efficient pumps, which we have, modern generation of pumps, they consume less electricity for same pumping capacity. That's why, in general, just mute one participant. That's why, in general, what we see right now for new buildings, for new district heating networks, which work, let's say, on the renewable sources of energy, the available pressure drops for calculations are being increased up to 30, sometimes 35 pascal both sides. Because the temperature differences between primary and secondary are also getting lower, and this requires higher velocities in the heat exchangers in order to make the optimal heat transfer. And in general, trend is going for like slight increase of the pressure drops available for the like primary and secondary side because of higher efficiency, energy efficiency of the pumps themselves. So of course, if you double the pressure drop, that's already something you will see in your, let's say, bill. But if you put it just 10%, yeah, that's something which will be very hard to see in your expenses. So any more questions? It seems none. So it's in that case, if you have any more like things you would like to get clarified upon, you can address, as I said, the questions to Marko, Agres, or Gintaras, and they will pass it over to me. I'll reply. If this is more like complicated topic requiring some training or webinar, we'll as well arrange that. And yeah, when in 2021 we'll have our Hex Selector up and running and available for you, separate training sessions will be arranged so you know how to use this tool properly and actually have all the benefits of it. Then, speaking that, I think the recording will be available later on for you of this webinar, and you can always address it if you have some questions. And then I would like to close right now this webinar. I wish then everybody basically good Christmas holidays and Happy New Year. And yeah, all the best for all of you.
Thank you, Mark. Have a nice day.